Have you ever noticed something weird about older apartment buildings? Especially in a lot of older neighborhoods. You walk around and see building after building that all look kind of similar. 5 floors, maybe 6 floors, lots of walls, small rooms, narrow hallways. And if you compare them to modern apartment buildings, the difference is obvious. Modern buildings have open floor plans, bigger living rooms, fewer walls, larger windows, more flexible layouts, and they can go much taller. So what happened? Were engineers in the past just less advanced? Did architects simply hate open spaces? Not really. There was actually a very practical reason these older buildings were built this way. And that reason is something called mixed structure. Now I know that sounds boring and technical, but stay with me, because once you understand this system, you'll start looking at older buildings completely differently, and you might even understand why knocking down the wrong wall in an old apartment could be a disaster. A lot of people think buildings are simple. They imagine a building is basically just some walls, some floors, a roof, done. But structurally, buildings are like giant machines. Every part has a job. Floors carry people and furniture. Walls carry loads. Columns transfer forces downward. Foundations send everything into the ground. And all of these parts need to work together. If one important piece fails, that load has to go somewhere else. And that's when things can go very wrong. Now, today, many buildings use one primary structural system. For example, reinforced concrete frame structures, steel structures, shear wall systems, full concrete systems. These are common in modern construction. But decades ago, especially when cities needed housing quickly and cheaply, engineers often used a hybrid solution. That's where mixed structures became extremely popular. So what exactly is a mixed structure? Very simple. Different parts of the building are made from different materials. For example, the floor slabs may be reinforced concrete, while the walls might be masonry. And sometimes certain vertical load-bearing elements are masonry as well. So instead of relying on one material for everything, the building combines multiple materials to do different jobs. Think of it like building a sports team. You don't want 11 goalkeepers. You want players with different strength. Same idea here. Concrete is great for floor slabs. Masonry walls can be cheap and strong under compression. Combine them together, you get a relatively affordable building system. And that's exactly why this structural type became so common, especially during rapid urban development. Governments needed housing, developers needed speed, cities needed density, and people needed homes fast. Mixed structures checked a lot of boxes. They were cheaper than full reinforced concrete systems. They were simpler than steel structures. They didn't require highly specialized construction techniques, and materials were widely available. Bricks? Easy to find. Concrete? Easy to produce. Labor. Workers already understood how to build these systems. That made mixed structures incredibly attractive, especially for residential buildings. And that's why so many older apartment buildings ended up looking very similar, because they were built using similar structural logic. But mixed structures also had limitations, big ones. And this is where things get interesting. One major issue was height. These buildings usually worked best for low-rise construction, typically under 6 floors. Why? Because masonry walls are strong when carrying vertical loads. They're great when weight pushes straight downward. That's compression. Brick and masonry handle compression pretty well. But buildings don't only face vertical loads. They also face lateral forces, wind, ground movement, earthquakes, uneven settlement. And that's when things get tricky. As buildings get taller, lateral forces become more important. A taller building behaves differently. It sways more. It experiences greater force demands, and pure masonry components start becoming a limitation. That's why mixed structures were often used in small apartment buildings, low-rise offices, older residential blocks, school buildings, small commercial buildings. Once developers wanted taller buildings, they needed better systems. That's when reinforced concrete frames became more dominant, and later, even more advanced systems took over. But back then, mixed structures were the practical solution. Not glamorous, not futuristic, just practical. And honestly, engineering is often like that. People think engineers are constantly trying to build the tallest, coolest thing possible. Sometimes that's true, but most of the time, engineers are trying to solve one simple problem. How do we build something safe that people can actually afford? That question shaped entire cities, and mixed structures helped answer it for decades. But here's where things get even more personal. You may actually live in one of these buildings right now and not even realize it. If your apartment building is older, if the rooms feel boxed in, if there are thick interior walls, if renovation rules are extremely strict, there's a decent chance the building uses some version of this structural concept. And that leads to one huge mistake people make during renovations. They assume every wall can be removed. Big mistake, huge mistake. Some walls in these buildings are doing serious structural work. Remove the wrong one, you're not just redesigning your apartment, you're potentially damaging the entire building's load path. And yes, that has caused real disasters in different parts of the world, all because someone thought, this wall is ugly. In the next part of this story, we need to talk about why these buildings often feel cramped and full of walls. And it all comes down to one thing: where engineers decided to place the load-bearing walls.
So now we know why mixed structures became so popular. They were affordable, they were practical, and they helped build massive amounts of housing fast. Sounds great, right? Well, there was a trade-off. Actually, a pretty frustrating one if you've ever lived in an older apartment. You know that feeling when you walk into an old unit and immediately think, why is this layout so weird? The living room feels small. The bedrooms feel boxed in. The hallway somehow takes up way too much space. There are random walls everywhere. And sometimes you look at the layout and think, who designed this? Did they hate natural light? Did they hate open kitchens? Did they hate big bedrooms? Not exactly. The real reason is structural. A lot of those annoying walls, they weren't added because architects loved tiny rooms. They were added because the building literally needed them to stay standing. That's the reality of mixed structures. In modern frame buildings, columns and beams do most of the heavy lifting. That gives architects a lot more freedom. Want an open living room? No problem. Want fewer walls? Usually possible. Want huge windows? Much easier. Because the structural load is concentrated in beams, columns, and core walls. But mixed structures are different. In many of these buildings, the walls themselves are doing major structural work. They're not just dividing rooms, they're carrying loads from the floors above. That means every wall placement matters a lot. Think about stacking books. If you stack one book directly on top of another, the load goes straight down. Pretty stable. Now, imagine removing books randomly from the middle. Everything becomes unstable very quickly. That's basically what happens when structural walls are poorly placed, or worse, removed. And this is why older mixed-structure buildings often feel very rigid in design. Architects had far less flexibility. They couldn't just place rooms wherever they wanted. They had to design around structural walls. And that brings us to one of the biggest design decisions in mixed structures. Where do you place the load-bearing walls? This decision changes everything: room sizes, building stability, construction cost, future renovation possibilities, and even earthquake performance. Engineers generally had two major choices. They could place walls mainly in one direction or in another direction. That decision created two common systems, and each one came with pros and cons. Let's start with the first one. Transverse wall system. This is often called horizontal wall load bearing. In this setup, floor slabs are directly supported by walls that run across the shorter direction of the building. Imagine slicing a building into multiple sections. Each section is separated by structural walls. Floor slabs rest directly on those walls. This setup creates strong lateral stiffness, and that's a big advantage. When wind pushes against the building or when minor seismic forces hit, the structure tends to resist movement better. It feels more stable, less side-to-side movement, less deformation. Engineers loved that, especially in areas where structural stability was a major concern. But there was an obvious downside. Room width became limited because those walls had to appear frequently. And once you keep inserting structural walls everywhere, you start creating smaller spaces. That's why many older apartments have narrow bedrooms, small living rooms, awkward layouts, limited open space. And renovation? Good luck, because many of those walls are untouchable. People often discover this during remodeling. They hire a contractor, they point at a wall, and they say, "I want this gone." Then the engineer shows up and says, "Absolutely not." And suddenly the renovation dream dies right there, because that annoying wall might be holding up multiple floors above you. That happens more often than people think. And it gets worse when people ignore professional advice. There have been real cases where illegal renovations caused cracks, serious structural damage, and in extreme situations, partial collapses, all because someone wanted a bigger kitchen. And honestly, that's a terrible trade. A bigger kitchen is nice. A collapsing building is not. Now, despite these layout limitations, transverse wall systems were incredibly common. Why? Because they worked. They were structurally reliable, they were relatively simple, and they matched the housing needs of their time. Remember, decades ago, many developers weren't trying to create luxury open-concept apartments. They were trying to house as many families as possible, fast, cheap, safe enough. That was the priority. And for that goal, this system made a lot of sense. But engineers eventually wanted more flexibility. They wanted larger spaces, bigger room spans, more adaptable layouts. That led to another approach, and that's where things start getting more interesting, because the next system gave architects more freedom, but it also created new structural risks.
So, in the last part, we talked about transverse wall systems. Super stable, pretty straightforward, but also kind of annoying if you actually live inside one. Too many walls, small rooms, limited layout flexibility. And if you want to renovate, you quickly find out the building says absolutely not. So engineers started asking a different question. What if we could create larger rooms without making the building insanely expensive? Because let's be honest, people don't love feeling like they live inside a maze. Families wanted bigger living spaces. Office buildings needed larger open areas. Developers wanted layouts that felt less cramped, and architects were tired of being told, "Sorry, another structural wall needs to go here." That's where longitudinal load-bearing systems started becoming attractive. This system flips the structural logic. Instead of floor slabs resting directly on transverse walls, the loads are first transferred to beams. Then those beams transfer the loads to longitudinal walls. So the load path becomes a little longer. Floor slab to beam to wall to foundation. That extra beam layer changes everything. Why? Because now you don't need structural walls cutting across every room. That means larger spans, and larger spans mean bigger spaces. Suddenly, architects had more breathing room. Living rooms could get larger. Bedrooms could feel less cramped. Office spaces could become more usable. Hallways didn't need to feel like narrow tunnels anymore. And developers loved this because bigger rooms are easier to sell. Nobody walks into an apartment and says, "Wow, I wish this living room was smaller." People want space. Always. And this system could sometimes stretch room widths to around 6 meters. At the time, that was a pretty meaningful improvement. It gave buildings a more modern feel compared to older layouts. And for homeowners today, these buildings often feel noticeably less claustrophobic than older transverse wall buildings. So, problem solved? Not exactly. Because engineering is full of trade-offs. Every time you improve one thing, you often weaken something else. And that's exactly what happened here. While longitudinal systems improved layout flexibility, they typically reduced lateral resistance. In simple terms, the building became less resistant to sideways forces. That matters more than people think. Buildings don't just deal with gravity. They also deal with wind loads, ground shaking, vibrations, small structural movements, temperature-related expansion, foundation settlement. And when a building has weaker lateral resistance, those forces become harder to control. Think of it like carrying groceries. If you hold a heavy box tightly with both arms, very stable. If you balance it awkwardly with one hand, much less stable. That's basically the difference. The transverse wall system had stronger sideways resistance. The longitudinal system gave you bigger rooms, but reduced that resistance. In seismic regions, this became a bigger concern, because earthquakes punish structural weaknesses very quickly. A building might look perfectly fine during normal daily use. Then an earthquake happens for a few seconds, and suddenly design weaknesses become very obvious. That's why engineers had to be extremely careful when using longitudinal systems. They couldn't just chase larger spaces and ignore safety. And this is where structural design gets interesting. Good engineers are constantly balancing competing priorities: cost, safety, speed, usability, flexibility, architectural needs, material limitations. There's rarely a perfect solution. It's usually about choosing the least bad compromise. And that's exactly what mixed structures represented. They were compromises that matched the needs of their time. Affordable housing? Yes. Reasonable structural performance? Yes. Perfect flexibility? No. High-rise capability? Definitely not. And there was another major issue. People often assumed these systems were stronger than they actually were. That overconfidence created problems, especially during renovations. Someone buys an older apartment. They want an open kitchen. They want a bigger master bedroom. They want modern design trends. So they call a contractor and say, "Can we remove this wall?" And sometimes the contractor says yes way too quickly. That's dangerous. Because in longitudinal systems, even if there are fewer structural walls, those remaining walls become even more critical. Remove one without proper structural reinforcement planning, you can seriously damage the load path. Cracks may start appearing. Floor deflection can increase. Doors may stop closing properly. And in worst-case scenarios, you create serious structural risk. This is why structural renovations should always involve engineers, not just contractors with confidence and a sledgehammer. Confidence is not a structural calculation. And social media renovation videos make this problem worse. People watch 30-second clips of dramatic wall removals and think, "That looks easy." What they don't see is whether that wall was structural, or whether the owner just created a very expensive future disaster. Now, by this point, you might think, okay, mixed structures already have height limitations. They also have layout limitations, and some versions have weaker earthquake resistance. So, how did engineers keep these buildings safe? That's where small structural details became incredibly important. And in many cases, those tiny details made the difference between survival and failure.
At this point,
Mixed structures might sound like a compromise machine. They're cheaper than full concrete frame systems. They're easier to build. They help solve housing shortages. But they also come with real limitations: height restrictions, layout restrictions, and in some configurations, weaker seismic performance. So the obvious question is, how did engineers stop these buildings from becoming disasters? The answer is something a lot of non-engineers completely overlook: small structural details. And honestly, this happens in almost every field. People notice the flashy stuff: the giant skyscrapers, massive bridges, crazy architectural designs. But real engineering often comes down to boring-looking details that quietly prevent catastrophe. Mixed structures are a perfect example, because without proper reinforcement details, these buildings can fail much faster under stress. Let's start with one of the most important elements: ring beams. These are reinforced concrete beams placed around the building horizontally. Think of them as giant belts wrapping around the structure. Their job is to tie the walls together. Without them, walls can behave like isolated pieces. That's bad, very bad, especially during earthquakes. When shaking happens, isolated walls may crack separately. They may shift independently. And once structural elements stop working together, failure can fast escalate. Ring beams help create structural unity. Instead of separate walls panicking individually, the building acts more like one connected system. And connected systems usually perform much better under stress. Think about carrying a couch. If 4 people lift together in coordination, it works. If everyone moves in random directions, someone's getting injured. Same idea. Now let's talk about another major element: structural columns. These are often added at critical locations, especially at wall intersections, corners, weak zones, and places where stress tends to concentrate. Their purpose is to strengthen areas that might otherwise become failure points. Because corners and wall joints are often vulnerable. When forces move through a building, those locations can experience concentrated stress, and stress concentration is where cracks love to begin. Once cracks begin spreading, problems escalate quickly. Structural columns help reduce that risk. They improve integrity, they improve force transfer, and they help prevent local damage from becoming total collapse. Again, not flashy, but incredibly important. Now let's talk about one area engineers pay very close attention to: stairwells. And this surprises a lot of people. Most people think staircases are just circulation spaces. You go up, you go down. That's it. But structurally, stair areas can become dangerous weak points. Why? Because stair openings interrupt floor continuity. You're basically cutting large holes into floor systems. That already creates structural challenges. Then, during earthquakes or heavy movement, stairs can behave differently than surrounding structural elements. This can create something engineers sometimes describe as a whiplash effect. Certain portions of the structure move differently than others. That difference creates concentrated damage, and stair zones can get hit hard. That's why engineers often place additional structural columns around stair areas. They're reinforcing vulnerable spots before problems happen. And this is a huge engineering lesson. Great design isn't just about making strong major components. It's about identifying weak links. Because structures usually fail at their weakest points, not their strongest ones. A chain doesn't break at its strongest link. Buildings work the same way. And history has proven this repeatedly. In many earthquake investigations around the world, engineers often find similar patterns. The building itself may have had decent overall design, but poor detailing caused catastrophic failure. Weak connections, poor reinforcement placement, missing structural ties, bad construction quality. Those small issues suddenly become life and death issues. And this is why building codes keep evolving. Every major structural failure teaches engineers painful lessons, and those lessons often become future regulations. Someone made a mistake, a building failed, people studied it, rules changed. That cycle has repeated throughout engineering history, and modern codes are often written in blood. That sounds dramatic, but it's true. Many regulations exist because previous failures showed what happens when details are ignored. And mixed structures are especially dependent on these details because they rely on multiple materials working together. Concrete behaves one way, masonry behaves another. Connections become incredibly important. If those connections fail, the entire system gets weaker fast. And this is why two buildings that look identical from the outside may perform very differently. One might survive decades, the other may develop serious issues much earlier. The difference often comes down to construction quality and detailing, not appearance. And that should make every homeowner think carefully before doing major renovations. Because many people only notice walls. They don't think about hidden structural details. They don't think about load paths. They don't think about reinforcement systems. They just think, I want an open kitchen. Again, hire structural professionals before making major changes. Pinterest is not a structural engineer, and neither is your cousin who knows construction. Now that we understand how engineers kept mixed structures alive, we need to talk about why these systems slowly started disappearing from modern construction.
So far, mixed structures sound like they had a pretty solid run. They were cheap, they were practical, they helped cities build huge amounts of housing fast, and with the right structural details, ring beams, structural columns, reinforced connections, they could perform reasonably well for low-rise buildings. For a while, this system made perfect sense, and honestly, it helped shape entire cities. A lot of older apartment neighborhoods you see today probably wouldn't exist without mixed structures. But then, construction started changing, and mixed structures slowly began losing relevance. Why? Because the world changed, and buildings had to change with it. Let's start with the biggest reason. People wanted taller buildings. This was huge. As cities grew, land became more expensive, urban populations exploded. Developers realized they couldn't keep spreading outward forever. They needed to build upward. That's where mixed structures started struggling. Remember, these systems usually work best for buildings under 6 floors. Once you go taller, structural demands increase fast. Vertical loads increase. Lateral forces become more serious. Wind becomes a bigger issue. Earthquake design becomes more complicated, and masonry components become a bigger weakness. At some point, engineers started saying, this system just isn't worth pushing any further. That opened the door for reinforced concrete frame systems. These systems could go taller, much taller, and they handled modern urban growth far better. Then came another problem. People wanted better layouts. This was a massive shift. Older generations were often focused on basic housing access. Having a home at all was the priority. But later generations started caring more about quality of life, and that changed everything. People wanted larger living rooms, open kitchens, fewer walls, bigger windows, flexible office spaces, parking garages, commercial space on lower floors. Mixed structures struggled with all of this. Too many structural walls, too many layout limitations, too much rigidity. Modern buyers didn't want to feel trapped in tiny box-shaped rooms, and developers follow demand, always. If buyers want open layouts, developers build open layouts. That pushed frame systems even harder. Then there's earthquake safety, and this became a bigger deal over time. As engineering knowledge improved, we learned more about how buildings behave during earthquakes, and engineers became much stricter. Older mixed structures could perform adequately in some situations, but many older designs simply didn't meet newer seismic expectations, especially poorly built versions, and construction quality was sometimes inconsistent. That's a dangerous combination. So, newer structural systems became more attractive because they allowed engineers to design for stronger seismic performance. Then, technology improved. This is a big one people forget. Construction tools got better, engineering software got better, material science improved, concrete technology improved, steel manufacturing improved, labor skills improved. What was once expensive became more affordable. What was once complicated became more standard. That made modern structural systems much more accessible. In the past, mixed structures made economic sense partly because alternatives were harder. That advantage slowly disappeared. And then there's speed. Ironically, the system that once helped cities build quickly eventually became slower compared to modern methods. Today, you have prefabrication, modular systems, advanced formwork systems, faster concrete placement methods, better cranes, better logistics. Modern construction became incredibly efficient, and mixed structures started feeling outdated. But here's something important. Just because a system becomes less common doesn't mean it was bad. People love judging older engineering choices with modern standards. That's unfair. Engineers work with the technology, economics, and needs of their own time. 100 years from now, people may laugh at some of our current building methods too. That doesn't mean today's engineers are stupid. It means engineering keeps evolving. Mixed structures solved real problems during critical periods of development. Millions of people lived safely in these buildings. Many still do. That matters. And if you travel through older cities around the world, you'll still see these buildings everywhere. They're part of urban history. They represent a specific era of engineering priorities. Affordable, fast, practical. Not glamorous, but necessary. And in many places, they're still standing because engineers made smart decisions within their limitations. That deserves respect. But there's one final lesson here that goes way beyond mixed structures, and it might completely change how you look at buildings forever.
After everything we've talked about, why mixed structures became popular, why they created awkward layouts, why engineers had to carefully balance stability and flexibility, and why modern construction slowly moved away from them, there's one final lesson that matters to almost everyone, especially homeowners. And honestly, it's surprisingly simple. Just because a wall looks ordinary doesn't mean it is. This is where people get into trouble. A lot of people buy older apartments and immediately start dreaming about renovations. They watch home makeover videos online. They see giant open kitchens, massive living rooms, beautiful open layouts, and then they walk into their own older apartment and think, why do I have so many walls? And that frustration often leads to dangerous decisions. Someone points at a wall and says, "This one has to go." That sentence has caused a lot of structural headaches. Because in mixed structure buildings, walls often do far more than people realize. They may be carrying floor loads. They may help resist lateral forces. They may connect structural systems. They may be part of the building's overall stability. And removing one without understanding the structure can create serious consequences. Sometimes the warning signs show up quickly. Cracks start appearing. Doors stop closing properly. Floors feel uneven. Walls begin separating. Neighbors start noticing strange issues. And sometimes the consequences take years to appear. That's what makes it scary. Structural damage doesn't always happen dramatically. Sometimes buildings fail slowly, quietly. Small damage accumulates over time until it becomes a major problem. And by then, fixing it gets very expensive or impossible. And it's not just homeowners. Bad contractors can make things worse. Some contractors promise fast renovations without proper engineering review. They say things like, "Don't worry, we do this all the time." That sentence should make you nervous, because structural design is not guesswork. It's math, it's analysis, it's load paths, it's understanding how forces move through a building. And that requires qualified engineers, not overconfident shortcuts. And this problem gets amplified by social media. You've probably seen renovation videos where someone smashes walls with dramatic music playing in the background. Everyone cheers, dust everywhere, looks exciting. But what you don't see is whether that wall was structural, and you definitely don't see the engineering drawings. Demolition is easy. Structural responsibility is harder. And this lesson applies beyond renovations. Most people judge buildings based on appearance. They notice fancy glass exteriors, luxury lobbies, cool architecture, tall towers. But structural engineering is mostly invisible. The most important parts of a building are often the parts nobody notices: the hidden reinforcement, the structural connections, the load paths, the foundation design, the boring details that quietly keep people alive. And mixed structures are a perfect example of this invisible engineering. From the outside, many of these buildings look simple, even outdated, but behind those plain walls is a huge amount of structural logic. Engineers were balancing limited budgets, material constraints, rapid housing demand, construction limitations, safety concerns, and long-term durability. That's not easy. And while modern systems may be more advanced, they're standing on lessons learned from older systems like these. Engineering evolves by solving old problems and creating better solutions. That's how progress works. And honestly, mixed structures tell a bigger story about cities. When you look at older apartment neighborhoods, you're not just seeing buildings, you're seeing economic history, population growth, housing shortages, material limitations, engineering compromises, urban expansion. Every old building tells a story about what a city needed at that moment in time. And mixed structures helped millions of families find homes during periods when speed and affordability mattered most. That's a huge legacy. So, next time you walk into an older apartment and think, "Why are there so many random walls?" Now you know. Those walls may be inconvenient. They may ruin your dream kitchen layout. They may make your apartment feel outdated. But they may also be the reason the building has stayed standing for decades. And that's a pretty good trade, because at the end of the day, the best building is not the one that looks coolest. It's the one that keeps doing its job year after year without collapsing on the people inside.